All right, we're going to talk about the mass or the density of gas lab here in just a second. I want to first talk about the density of liquids. We went through all these answers in the previous video, but I do want to talk about the histogram. So you should have had a data table like this. Attached in the density of liquids, and you were supposed to make a histogram out of it. This is what the histogram should look like. You can clearly see, now I put liquid 1 and liquid 2 instead of solution 1 and solution 2 because we use different liquids. But you can clearly see that you've got almost all the liquid 1s over here and almost all the liquid 2s over here. There's a few that aren't. Okay, these 3 here, I would say somebody made a mistake. But that's what your histogram should look like. Notice I've got a title here at the top, density of liquid histogram. And this histogram needs to be taped into this section right here, the density of liquids. So let's turn the page and let's look at the next section, the density of a gas. I want to go over these answers. You're going to need to make a histogram out of this data too, but we'll show you that here in a second. So for the density of a gas lab, which you did on either Monday or Tuesday, here are the answers to the blue questions. The first question says, why is it important to hold your mouth across, sorry, let me read that again. Why is it important to hold your hand across the mouth of the bottle while removing it from the container? Well, the reason why we wanted to do that, so here's blue question number 1. We'll say this. The water in the container is our final volume. If you didn't hold your hand across it, the water's going to spill out and we wouldn't be able to measure the final volume. Then it says turn the bottle upright and find the volume of water that's been displaced by the gas. How is this volume related to the volume of the gas? So BQ2, I'm just going to say it is.
Pardon the interruption. Just making an announcement. If your neighbor's not nearby and hearing this, make sure that they know. We will be meeting in the library at 2 o'clock today. We're going to meet in the library at 2 o'clock. So in about an hour and a half, we're going to meet in the library and debrief a little bit before it's time to get out of here today.
Number 3, it says, how can you find the mass of the gas? You're going to take initial mass minus final mass. That's going to give you mass of gas. Then number 4, what's the density of the gas? I'm going to tell you what it should be. I don't know what you got, but it should be 0.0018 grams per cubic centimeter. And then number 5, what assumptions have you made in using this method? Well, there's a couple things we've assumed. First of all, mass is conserved. We know from last chapter that as long as we have a closed system, that mass should be conserved. And so as long as there wasn't any leaks or anything, then the mass we started with, we should have ended with. And so this change from initial mass to final mass, that has to be the gas that escaped into the other container. Okay, the other thing we're assuming is that the gas does not dissolve in water. Okay, and we'll deal with those assumptions a little bit later. So let's move over to 17 through 22. Number 17, and let me erase all this. 17 says, which of the following choices represents the approximate ratio of the density of the gas? In experiment 3.7, the density of water, which is 1. Well, the ratio is 1/1000, letter A. Gases are about 1,000 times smaller than the density of liquids. Number 18, a mixture of two white solids is placed in a test tube, and the mass of the tube and its contents is 33.66. The tube is stoppered, and the apparatus is set up to collect any gas produced. When the tube is gently heated, a gas is given off, and its volume is found to be 470. After the reaction, the mass of the test tube and its contents is found to be 33.16. What's the mass of the gas collected? So I'll put letter A over here. All we're going to do is take the mass before minus the mass after. So 33.66 minus 33.16 gives you 0.50 grams. And then what's the density of the gas collected? Well, we've got mass right here. We have volume right here. We just have to calculate it. So in letter B, here's the equation. M is equal to V times D. So 0.50 is equal to 470 times D. So divide both sides by 470. And you get the density is 0.0011 grams per cubic centimeter. So I'm going to erase 17 so I can move this up a little bit. So number 19 says experiment 3.7, the density of a gas is repeated with the same or with a sample of a different solid. Here are the data obtained. So they've got the mass before, the mass after, and the volume. Could this gas be the same as that which was produced in experiment 3.7? We know the stuff in 3.7 has a density of 0.0018. So let's figure out what the density of this is. So if we do a little math here, if we take, to find the mass of the gas, 35.40 minus 34.87, you get I better do that here. 35.40 minus 34.87, you get 0.53. That's the mass of the gas. They tell you the volume of the gas right there. So we can use this. M is equal to V times D. So 0.53 is equal to 480 times D. Divide by 480. And you get D is 0.0011. The stuff we had in our density of a gas lab was 0.0018. So could it be the same? The answer is no. Make sure you have this down too. That's the work for number 19. Number 20. The volume of gas generated by treating 1 gram of baking soda with 8.8 grams of sulfuric acid is 200 cubic centimeters. The remaining acid and solid have a mass of 9.4. So that's the mass after. The mass before is this baking soda with the sulfuric acid, 1 plus 9.8. 1 plus 8.8 gives you 9.8. So what's the density of the gas? So if we take, the mass is going to be 9.8 minus 9.4, which gives you 0.4 grams. To find the density, we use this. Mass is equal to volume times density. So 0.4 is equal to 200 times D. Divide both sides by 200. And you get the density is 0.002 grams per cubic centimeter. On number 21, it kind of continues with number 20. It says if the volume of the gas in question 20 is compressed to 50, what will be the density of the gas now? So before we go on, let's do that real quick. So the first part of 21, we know the mass is going to stay the same, so M is equal to V times D. So 0.4 is equal to 50 times D. Divide both sides by 50. And you get the density is 0.008 grams per cubic centimeter. So that's the first part of 21. Then it says, to what volume must the gas be compressed before it reaches a density of 1, which is the typical density of a liquid. So here's the equation. We know the mass is 0.4. We're trying to find the volume, and we want to know what it would be if the density is 1. So divide both sides by 1. I guess I should cross those off. And you end up with a volume of 0.4 cubic centimeters. And number 22, I'll put over here. It says the gas whose density you measured in experiment 3.7 dissolves slightly in water. How does this affect the volume of the gas you collect? It's going to, so on letter A, it's going to make the volume lower than what it should be. And then letter B, how does this affect your determination of the density of the gas? So on B, mass is going to stay the same. And so to make mass stay the same, if volume goes down, then density goes up. So most of you probably had a density greater than 0.0018. And we're going to look at that here in a second. So that's the answers to all the questions in the density of gas lab. Now let's look at the histogram. So you should have this data table here attached in the density of gas lab, and we want you to make a histogram out of it. Now we've got some very, very small numbers. So if you look, see if I can get that all up there. You've got some outliers here, like this one. What is that? Tenths, hundreds, thousands, 10 thousandths, 100 thousandths, millionths. So 55 millionths is a lot smaller than all the rest of these. There's a lot of 0.20s, 0.21s, 0.3s, stuff like that in there. Remember, 0.002 is the same as 0.0020. So here's the way that I would do it. Draw a line across right here. And instead of writing all these zeros, let's just say the main thing we want to get to the 10 thousandths place. So I'm going to put 10 thousandths place. And we really don't have to go much below 0.1. So I'm going to call this over here 10, and I'm going to go up by 2 10,000ths. So that would be 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52. So 12 10 thousandths would be this number, 0.0012. So that's what we're looking at. So let me start. I'll do the first three for you. So 0.002 is the same as 0.0020. So it's on this boundary. It's going to fall to the right. We do it just like that. 0.0016, it's on this boundary. 0.0021 is right here. 0.0025 is right here. And so on. If you come all the way down here to this one's not on here. It would be way over here someplace. So make sure you have that histogram done today. You also have, you grab it here. This worksheet that I gave you in class, if you don't have it in class, there should be a link on there that says density worksheet. And I need the answers to one of these questions on Canvas. So make sure you fill in the text box with your answer to one of those problems. Okay, read the directions on Canvas for that. That's what you need to have done by the next time that you come to class.